Class, this is the calorimetry guided notes video. I just want you to know I referred to it as calorimetry, so I'm going to call it that, but also it falls under the concept of thermodynamics, okay? So most of this is going to be thermodynamics, and we'll focus on the calorimetry part, which is going to be towards the end. I apologize if this has to be multiple videos. I just have a very sick kiddo and another kiddo who's just going crazy. So I apologize if it has to be multiple videos. Okay, so at the top right here, I have a list of some terms. Most of these terms you probably have already seen before, but I just want to walk you through some little misconceptions students have, and we're actually going to focus on the bottom of this page here, okay? So exo and endothermic, we've already talked about those from first semester. It's just a reaction that will release energy or a reaction that will absorb energy. It's not even so much that the reaction will absorb, it definitely will release, but a reaction that requires energy in order to go, okay? So therefore, if it requires it, it's going to have to absorb the energy for the reaction to happen. So anyway, so just be mindful of that. Kinetic and potential energy, that's more of a physical science term, but in chemistry, we look at it as is the substance undergoing a change? Is the substance moving? Is the substance... when I say moving, like, are the atoms and stuff getting more disordered, or are they kind of coming back together in a more ordered state? So potential and kinetic energy, we'll be tracking with all of those, but the easiest way of remembering it is kinetic energy is associated with motion, something happening, something's happening, I guess. Potential energy is something's not necessarily moving or getting closer or farther away or faster, but it just because of where it is or what's around it, it's considered stored energy because in a moment it can all of a sudden change, and then that potential energy converts to kinetic energy, and it's energy that we observe. So it's hard to observe potential energy, but since we know energy is conserved, not necessarily created, that's a physics concept. We just refer to it as potential energy. So even though we can't see it, we know it's there just by its position, orientation, all those things. Okay, heat and temperature. Students tend to get those two confused. So heat is the actual transferring of energy. Temperature is just a data point reading of how much energy is in the substance, okay? Specifically kinetic energy. So once again, temperature, and I think of it as like literally having a thermometer. So I would not know the temperature unless I put the thermometer in there. It's a data reading. Heat is the actual, like, you see the vapors kind of coming off of something, even though that's considered vapor, but it is kind of heat. The heat is the actual something that's happening. It's the doing, if you will, of the energy. So the transferring of energy is referred to as the heat, and the temperature is just a data reading, okay? Okay, so specific heat capacity, this is a new term for us. So it's the amount of heat required to change the substance's temperature by 1 Kelvin. So we've already talked about Kelvin, I believe, in our last unit. I'm trying to remember. I think we did, yes. So 1 Kelvin is different than Celsius and Fahrenheit, but a specific heat capacity. So it is a measurement, it is a characteristic, it is a property of a substance. And it's a numerical number, a property, and it's the amount of heat required to change the substance's temperature by 1 Kelvin. So, once again, this is a unique number, and we're going to we'll see how this plays out. But we tend to notate specific heat capacity with C. I know in the opening video, I don't even know what his name is on Crash Course, he used a little lowercase s. That's okay if you have that in your notes, but you'll just also want to know that people will commonly refer to it as the big C. And so if you glance down here to this heating curve, you'll see hopefully you can see my cursor, if not, no worries. This right here is the C that I'm talking about, okay? So specific heat capacity, it's a specific number to the substance, and it's the amount of heat required to change the substance's temperature by 1 Kelvin. Okay, vaporization, condensation, freezing, melting, those are all just states of matter, like phase changes. Calorimeter. So this measures the amount of heat involved in a chemical reaction or a process. Okay, so a calorimeter is literally an actual setup. There's two different common kinds of calorimeter. We have a bomb calorimeter and a coffee cup calorimeter. So, but bombs aren't really associated with bombs. But what I will say is, when you're thinking calorimeter, think of a styrofoam cup or a coffee cup, it doesn't matter, and you are putting foil over top it, okay? And you have a thermometer sticking through that foil on like the lid, if you will. So you have a styrofoam cup with some lid on top and a thermometer in there. That right there alone is a calorimeter. Now you might have a chemical reaction you might actually do a chemical reaction in that cup, and we will observe, okay, before the chemical reaction happened, the temperature reading was this, and then we put the stuff in there and let the chemical reaction happen, and we observe a different temperature. And so by having the temperature data point, having the mass, having the specific heat of certain things, we can therefore calculate kind of the energy associated, or the heat that happened with the reaction, okay? So a calorimeter is an actual kind of an equipment, but I would say you can make your own calorimeter, so it's not really a fancy piece of equipment. I don't know if you noticed, but I use this word heat and energy interchangeably. So just so you know, they are virtually the same thing. Heat is just a fancier term for the specific type of energy we're talking about, okay? So just be mindful of that. Okay, let's see. Enthalpy. So enthalpy is a new word. Enthalpy is the heat of the system. So enthalpy, I don't have it written here, but if you'll go ahead and write an H next to it. So we refer to enthalpy as a capital H. Now, I'm trying to see if I have writing abilities. Give me a second. Okay, H, capital H for enthalpy. But I also want you to put delta H. Wow, that does not look like a triangle. So it's supposed to be a triangle H, delta H. So enthalpy is the heat of a system, and it can be notated in multiple ways. So we consider enthalpy as H, but let me give you some more terms up here. So I told you calorimeter, or not calorimeter, specific heat. Where's specific heat? No, it's all the way up there. Oops. Okay. So enthalpy is the heat of the system, but how do we even calculate the heat of the system? Well, you calculate the heat of the system by adding up all the heat within the system. I know it sounds silly, but it's true, and that's what this heating curve I'm about to walk you through. So where was my heat? Right here. Okay, heat, we usually notate it with a little lowercase q. So heat is q. So if it says the change in heat or the change in enthalpy, it is now referring to that delta H. So H is enthalpy, Q is heat, C is specific heat, and delta H just means the change in enthalpy, okay? So once again, it's the heat associated with the system. Activation energy. So we'll see this on the next page, which I guess I can go ahead and slide over. But it is the energy required for the reaction to progress. So right here, I'm on the second page real fast, and I just wanted to show you. So if you're looking here at my little reaction curve, it is starting with F, or this little green line, okay? And I'm starting at F and I end with G. But rather than just going straight down, or rather than just gradually somehow curve down, we actually curve up. And so what that's showing you is that you actually have to input energy into the reaction for it to go, even though the energy associated with your products is lower, okay? So this little hump, if you will, on the top of the reaction curve is referred to as where the activation energy. So what is the exact activation energy? So you're starting out at this dotted line right here, and going to the top of the curve, that B arrow, would be your activation energy, okay? So that's the energy required for this reaction to occur. So that's just another term. Okay, catalyst. The last one would be catalyst. So this speeds up a reaction by lowering the activation energy. So just so you know, my students who are going to probably study science in college, catalysts are arguably one of the most confused or has tons of misconceptions associated with it for a catalyst. So let me just dive into it and hopefully I can debunk some of the thoughts. So a catalyst, and most of you probably already heard it before, lowers the activation energy required for the reaction to happen. Now, how that happens, it's a kind of a biochemical concept, but what it does is the catalyst in of itself usually, and it's kind of the concept of an enzyme, will create a scenario that the reactants will come together more frequently. So if that means there's a molecule floating around and it puts one reactant with another reactant, like just by attaching it to that molecule, well, therefore those reactants are much closer to one another than just floating around freely. And okay, give me a second. So therefore it doesn't require as much energy for the reactants to come together in order to form the products. So just so you understand, we observe a catalyst as lowering this curve right here, right? It lowers the requirement of activation energy. But what's actually happening in the reaction with the presence of a catalyst is it's bringing those reactants closer together, or it's making their collisions or the coming together much more frequent, easier, any of those terms, okay? So just remember, it's not just a curve, theoretical curve here. There's actually something happening, and the catalyst is just allowing those reactants to come together easier. Therefore, there's less energy required for those reactants to come together, okay? Which is why we say it's a lower activation energy. Okay, thank you for bearing with me. Heating curve. So this heating curve right here, we're going to apply some of these terms and these concepts to this. So the heating curve and basic calorimetry calculations would be the overall all you would need for this unit, okay? As for your test, I'm leaning towards a project, but don't be worried. It's not like a big project. It would be something associated with building a calorimeter at home or creating a heating curve. So let's dive into what is a heating curve. So this one right here, I usually sketch it based off of water because we all know some basic data points for the melting and vaporization of water. So heating curve is you're taking a substance and you're heating it or you're cooling it. So when you're heating it or cooling it, you have somewhat four, but I'll say three different options. So you are either solid, liquid, or gas, okay? So on this curve right here, we have to make sure we understand, first of all, what are we at the given point in terms of the state of matter, and we also need to understand the coordinates or the x and y planes. So this one right here, this is temperature on the y-axis. So temperature is very important for us to remember what temperature is, because if I am moving, so if I'm following along this line, this stair-stepped line, and I'm moving up at all, it could be at an angle, it could be barely moving up at all, but if I'm moving up, my y is changing, my temperature is changing. So we need to remember that, because when we have to recall the formulas associated with each little piece of this stair-step, we're going to need to recall the formula, but it's given based on the axis, okay? And then this one's time. So time just meaning as the reaction progresses, okay? So I chose to draw this as solid water, okay, being heated all the way to a gas. However, you could flip this stair step in any way, shape, or form, and you could be up here, and therefore I would have high temperature at the beginning, and I could slowly move down, okay, and I would be therefore ending with a lower temperature, which would indicate that obviously I'm going from a gas to a liquid to a solid. Okay, so anytime I try to color code it, anytime I'm climbing on my graph, my temperature is changing. In this case, because I'm climbing, because I'm increasing, my temperature is increasing. So first of all, I will say I am heating, okay? So that's a main concept right there. I'm heating by increasing not increasing temperature. By observing an increase in temperature, I am implying that the substance is being heated, meaning energy is being put into the substance. Okay, so I'm just kind of talking you through this. Any of the plateaus, any of these flat lines, okay, the temperature is not changing, as you can see. Sorry if I didn't draw it super flat, but it's implied that it's not changing. The temperature is not changing. However, my reaction is still progressing. So if my reaction is still progressing, we need to know, well, why did it just pause for a moment in its temperature? And the reaction kept going, and then all of a sudden it started to pick back up and heat up again. Well, these little plateaus are what we call phase changes. So what happened was the substance was no longer absorbing, it was still absorbing energy, but it was no longer increasing temperature. The energy was being utilized in something to do something else. And what it was doing was it was actually changing phases. So from left to right, if you're heating, you're going from a solid to a liquid. Over here, solid to a liquid, so I was melting. So my water, my ice was melting into water, okay? And there's a specific formula associated with that right there, okay? And then once again, once I'm in my liquid phase, so I tried to give you a little indicator as to where you were. So this first climbing little green leg of the graph, I was solid. Right here, I'm changing from a solid to a liquid. Once I pick back up on my climbing little green line, I'm now a liquid again, and I observe a temperature increase, so we know it's continuing to heat, and then all of a sudden I observe it stops changing temperature, but my reaction is still occurring, and then it decides to pick back up again. So what's happening here? Well, I know I'm reading it left to right, my temperature is increasing, so I'm going from a liquid to a gas, this vaporization, so my liquid water is now vaporizing off into steam. So this little plateau is the converting step, right? It's the phase change. So it's changing the states of matter. And then once it's in a gas, all of it's in a gas, it will now start climbing in temperature again. And it'll start climbing in temperature, meaning it's just getting the gas is getting hotter and hotter, okay? Okay, so that was the overall concepts. If you were to go the other direction, so usually we don't read these left to right, you would just be observing a curve kind of like this. Hopefully you can see my cursor. That would be a scenario where you're going from higher temperature to lower temperature. So you would be going from gas to liquid, which is condensation, and you would be going from liquid to solid, that would be freezing, okay? So other things that are on this graph, there's a lot going on here. So let's look at this melting point, boiling point, freezing, condensation point. So all of these points right here, where the plateaus begin and end, are where these things occur, okay? So let's read it from left to right here. So I'm a solid, and I'm all of a sudden about to melt. So this right here would be my melting point, okay? So let's keep reading it left to right. Okay, so now once I've melted, everything's melted, I'll start climbing again. And then I get to here. This is now what I would say my vaporization point, boiling point. Okay, so right here. So I went from a liquid and all of a sudden I'm starting to vaporize. So this would be my vaporization point, okay, or boiling point. Okay, so let's just read it in the opposite direction. So I'm a gas, and all of a sudden I stop being a gas and I'm going to start converting to a liquid. So this right here would be my condensation point, right? My gas is now converting to a liquid, so it's the condensation point, okay? And it keeps going, and then now I'm all liquid, and then I hit this point right here on my graph, and I'm going from a liquid to a solid, so this right here would be my freezing point. So if you see, the temperature reading is going to be the same. It's just having to do with the timing piece of the coordinate, okay? Okay, so now let's talk about kinetic and potential energy. Yeah, and then we'll talk about the formulas. Okay, so for kinetic energy, so we say this is actual, I say something's actually happening. Kinetic energy is a direct reading, and I think I even wrote it up here. Oh, it's energy in motion. It measures the energy associated with something moving, and so when something's getting hotter, or you can even say something's getting cooler, you're observing a change in the motion of those particles, okay? So the reason why I'm trying to tell you that is because there are certain pieces of this graph that you'll observe a kinetic energy change and then a kinetic energy constant. So anytime you're climbing on this graph, okay, whether you're going up or down, depending on how the graph is written, A change in temperature is going to be a change in kinetic energy because the particles are now changing their speed. We know particles are moving, and the hotter they are, the faster they're moving. So once again, anywhere on this climbing graph, kinetic energy is changing. But in this case, if you're heating it, so I'm just looking up here. So if you're heating it, you're getting hotter. Well, those molecules are going to be moving faster. So by heating a substance, your kinetic energy is going to increase. And it's consistent with every single leg on the graph. Opposite is true. So if you're cooling the substance, the speed of those particles are going to slow down, and so the kinetic energy is going to decrease anytime a decrease in temperature is observed, okay? Because remember, let's just play the little connect the dots. A temperature is just a reading of the heat, and the reading of the heat is just a measure of energy, and kinetic energy is the energy associated with particles moving. So that's how we're making all those connections, okay? Okay, so now any of these plateaus, we need to talk about potential energy. So what's happening on the plateaus is they're changing their states of matter. So their temperature is not changing, but we observe the temperature is not changing. So therefore, what we're going to say is the speed of those molecules are not changing. They're still moving, but they're not changing in speed. All they're doing is they're changing the state of matter. So they're going through, like, I don't know, kind of like how butterflies go through metamorphosis, I guess. So this one's kind of harder to grasp, I understand, so maybe just if you need to know it, just know it. But any kind of plateau on a heating curve, like right here, this is where potential energy is changing. But my kinetic energy is remaining constant, so there's still kinetic energy, but it's remaining constant because the speed of my particles are the same, but we are going to observe an increase or decrease in potential energy. Because it has to do with the orientation, the position, the structure of the particles or the atoms in that substance. And so by changing the orientation, therefore we're changing the potential energy. Okay, so heating, we are going to increase the potential energy. So by heating it, we're increasing the potential energy. And if we're cooling it, we're going to be decreasing potential energy. Let me think. Yeah, it might just be easier to memorize that. I don't want to confuse you guys with too much. So once again, if you are increasing, if you're heating at any point on a plateau, you're going to observe a increase in potential energy. And if you're undergoing cooling, then your potential energy is decreasing. So I understand that the temperature might not be changing, but I'm referring to the phase. So melting would be a phase of heating, right? Freezing would be a phase change of cooling. So that's what I mean by that for those potential energies. Okay, the last little layer, and then one little note about this. So the last little layer would be these formulas that I attached to each of the heating curves. So once again, just to remind you, this whole heating curve is just, I notated it as much as possible, but it's just tracking a substance being heated from a solid state all the way to a gaseous state. We're observing the temperature change. We're observing certain phases occurring at different times. And now we have these formulas, and I'm actually going to be able to calculate the amount of energy, specifically heat, associated with this heating process, okay? So any climb in temperature, so any climb on this graph is a change in temperature. You have this Q equals MC delta T. So it looks like MCAT, that's how most students memorize it. But Q stands for heat, equals M, which is the mass of your substance, okay? C is the specific heat for the substance, and delta T is the change in temperature, so T final minus T initial. I'm going to dive into these formulas, I think, over here, so don't worry too much about how to calculate them, as long as you understand what piece goes where. Okay, so Q equals MC delta T calculates the heat associated with just this climate temperature. Any of the plateaus. So the plateaus are a little bit more unique. The reason I say that is all of the climbing graphs, all of the points of climbing, change in temperature, are the exact same formula. Q equals MC delta T, Q equals MC delta T. The C is the same, it's that specific heat constant for your substance. But on all these little plateaus in your graph, you're gonna have a unique delta H, okay? So in this case, the heat is equal to, that little M is actually standing for moles. But I find a lot of like introductory chemistry classes just I think they changed the delta H to make it compatible with the with grams, but just be mindful. Usually it's written as moles because delta H is usually in a molar unit. So anyways, the takeaway is Q equals M delta H, Q equals M delta H for the plateaus. However, these delta H's are different. So we call this delta H fusion. So delta H fusion has to do with the process of solid to liquid or liquid to solid, okay? The Q equals M delta H vaporization has to do with the change in energy associated with this liquid to gas, gas to liquid phase, okay? And once again, I'm going to show you how to use all these calculations, but the takeaway point is anytime you're climbing on the curve, you are using Q equals MC delta T. Hopefully you can see delta T is the green, which is why it's increasing. And anytime you're on a plateau, you're going to use Q equals M. M usually stands for moles, and then the delta H, but it's going to be a different delta H for each plateau. Okay, the last little piece. I'm probably going to have to break up these videos. So when you're moving left to right on this, or it's more so just increasing, if you observe that this right here is going to be your heating, okay? Anything heating is going to be an endothermic process, okay? So if you are an ice cube, the only way that you are going to become liquid vapor or water vapor is by absorbing heat, right? You're cold, you're going to have to heat up in order to become a gas. So just so you know, any kind of heating process is something that we call an endothermic process, meaning it must absorb heat, which makes sense, the ice cube to the vapor. But an endothermic process is notated by positive delta H, okay? So that's really important, and we'll dive into that a little bit. Anytime you're cooling, so if you're a gas and you want to cool into a solid, well, you're going to have to release that heat because gases are moving around really fast, they're really disordered, and they're really hot. And so they're going to have to release their energy, release their heat in order to cool down and slow down to become an ice cube, okay? So anytime you're cooling, we're releasing heat. It's an exothermic process, and it's going to be negative delta H. Okay, let's see. Okay, I'm going to go ahead and pause this one video, and I'll break it up. So I'll make sure to make it clear as to what your assignment is for today. But thanks for tuning in, and I will talk to you guys.